Okay, so yesterday we defined the art-centered inertial frame, ECI frame. The notation for the ECI frame is I. Okay, and this frame is used as a reference frame. Okay, so you are interested in finding position, velocity, etc. With respect to this frame. The next frame that we'll consider is again art-centered, but it is fixed to the art. That's why it's called art-centered, art-fixed ECEF frame. Its notation is E. Okay. The coordinate frame origin is at the art center, which is taken as the center of the ellipsoid. We are going to define ellipsoid today. And then z-axis points along the art spin axis from the center of the ellipsoid to the north pole, and the north pole is taken as the IRS reference pole IRP, which we defined yesterday. It's the average position of the pole, north pole, surveyed between 1900 and 1905. And then x-axis points from the art center to the IRS reference meridian or 0-degree meridian. So if this is the center of the ellipsoid, then the z-axis along the IRP, IRS reference pole, and the x-axis points from the center of the ellipsoid to the 0-degree meridian or IRS reference meridian, and then the y-axis will make 90-degree angles with the x-axis, and is defined such that we have a right-handed orthogonal coordinate frame. Now, in this context, note that the IRS reference meridian is not Greenwich meridian, which means the reference or 0-degree meridian does not pass through Greenwich. Rather, it is about 102 meters east from the Greenwich Observatory. So let's try to understand quickly why the reference meridian does not pass through Greenwich. Okay, now for this purpose, we need to recall that time and longitude are interrelated. And we are also going to define a particular time called astronomical time. This time was determined by the Greenwich Observatory in the 19th century. So they used an optical instrument, basically a telescope, at the Greenwich Observatory. They used this telescope to determine the local vertical. How do we define the local vertical? So simply said, if we suspend a mass from some fixed support and make sure that it is not perturbed by any disturbances, then the direction it points to is the local vertical at that point. Okay. Now they determine the local vertical optically, okay, using the telescope. Okay. And then what they did, they identified a distant star, okay, and then they calculated the time between the successive transits of this star across the local vertical, again using the telescope. Okay. This time is nothing but the length of a day, right? Now, since they have taken a distant star which appears to be a point, the calculated time is highly accurate. So we got the length of the day this way, and if the length of the day is divided by 86,400, we get the length of a second, correct? So this is how our time was derived. And this time, because it was derived based on astronomical observations, is called astronomical time. Okay. Now we can also find the earth rotation rate from the length of the day, because we know 2 pi by t is equal to omega. So from that we can also find the earth rotation rate. So we got the reference time at the reference longitude. which was taken as the longitude at the Greenwich Observatory. Now next we can use this equation to find the time at different longitudes, right? So if t is the time at some other longitude, lambda, then we use this formula to find the time, local time at that longitude. So t naught is the reference time as at the reference longitude, which at that time was taken as the Greenwich longitude. This was 0 degree. Now you should also note that the vertical plane across which we are they calculated the transit time um, did not pass through the Earth center. Why? Shortly we will see that the Earth surface is modeled as an ellipsoid, not a sphere. Okay, so let's say this is the point at which the Greenwich Observatory is located, and this is the direction of the local vertical. Okay, and this is some other point at some other longitude. Now, if the Earth had been a sphere, this would have been the vertical, correct, normal to the surface, and this would have passed through the center of the Earth. So let's say this is the center of the Earth. Now, since Earth is not a sphere, rather it's an ellipsoid, the local vertical does not pass through the center of the Earth. So it passes through some other point, and this happens because the Earth is not a sphere. So the vertical plane that was used to derive this astronomical time did not pass through the center of the Earth. Okay. Then in the 1980s, advanced techniques were developed to determine Earth rotation rate. And we know that we can go back and forth between the length of day and Earth rotation rate. So given the Earth rotation rate, we can calculate the length of day, right? So different techniques like lunar laser ranging, where laser pulses were transmitted from the Earth and they got reflected back from the moon. And by calculating the round trip time of the return pulses, it's possible to determine not only the lunar orbit, but by using proper mathematical models and sophisticated techniques, one can determine Earth rotation rate. Okay. Similarly, satellite laser ranging, the same thing could be done with a satellite. Laser ranging was done. Then another technique called long baseline interferometry. Okay, very long baseline interferometry was used, where what they did, they installed antennas, okay, large antennas at different places on the Earth, and all these antennas receive signal from a particular star. Okay, such stars are well known. For example, quasars. So quasars are actually supermassive black holes. So they emit light at a particular frequency, and they can be easily identified. So the light, the electromagnetic waves from the same star were received by all these different antennas in different parts of the world, and they noted the time difference of arrival, TDOA, of the signals from the same star in different antennas. And actually the objective was to calculate the distances between the antennas. Okay, so they could precisely do that. In addition to that, if they follow some reverse procedure, it is possible to also find the Earth rotation rate. So they use different advanced techniques to determine the Earth rotation rate. Now all these advanced techniques assume that the meridian plane passes through the Earth center. Okay. Now to retain the same definition of the astronomical time, what was done is they shifted this local vertical at the Greenwich Observatory such that it passes through the Earth center. So the same line at the Greenwich Observatory is just shifted to make it pass through the Earth center. And it intersects the Earth surface at this point, which is taken as the 0 degree reference longitude. And it is this distance is about 102 meters. Okay. This is a pictorial representation. So actually, it is 102 meters east from the Greenwich Observatory. Any question? So have you understood why the 0 degree reference meridian is not over Greenwich? It is off from Greenwich.
Yes, ma'am.
Why I am receiving response only from one person?
Yes, ma'am.
Who else is there? I saw Nikita. Nikita is there?
Yes, ma'am.
Nikita and Nila, have you understood?
Yes, ma'am.
Nikita, are you there? Did not Nikita join? I think I saw her. So Nikita is not present actually. Ajita, you understood?
Yes, ma'am.
Okay, Nila, you understood, right? Nila is there?
Yes, ma'am.
And Murali, are you there?
Yes, ma'am. Yes, ma'am.
Okay, this frame is used as a reference frame, and it can also be used to resolve to find the components of a vector quantity. So that frame is called a resolving frame. It will be clear to you later. The third frame that we're going to define is called local navigation frame. Okay, the notation is N. Okay, the origin is at the vehicle's CG, center of gravity, or it could be a suitable point whose position we are interested in. Okay, so the origin is no longer at the Earth center now, and that's why it's called the local frame. Okay, now z-axis points downward along the local vertical. We defined local vertical on the previous slide. Okay, so let's pick this location. So the origin is here. Okay, and the z-axis points along the local vertical. Okay, and how do we define the x-axis? So we connect the origin, okay, with the North Pole along the surface of the Earth. So we get a curved line, correct? And then we take the plane which is normal to the z-axis. So it's basically the plane which is tangential to the Earth's surface, this plane. Okay. And then what we do, we take the projection of that curved line that we got by connecting this origin and the North Pole on this plane which is normal to the vertical axis, the z-axis. That line is actually the x-axis. In other words, x-axis points along local north. So this is the direction of local north at this point. So the x-axis points along the local north. Okay. And y-axis points along east, and z-axis points along down actually, along the local vertical. Okay, so this frame is also called NED frame, northeast down frame. NED frame notation is N. Another realization of the local navigation frame is east north up, which is not shown here. East north up. So in the NED representation, a north is the x-axis, east is the y-axis, and down, this is down. So down is the z-axis. So x, y, z. If you orient the fingers of your right hand, you will find that this is a right-handed orthogonal frame. So what you can do, one way is to use the right hand thumb rule, another way is to extend 3 fingers of the right hand such that the thumb is along the x-axis, the forefinger is along the y-axis, and the middle finger is along the z-axis. You just orient these 3 fingers of your right hand, you will find that this is a right-handed orthogonal coordinate frame, NED, northeast down frame. Now, if we want to have the x-axis along east, okay, and y-axis along north, then we cannot have NED frame. Rather, we should have east, north, and up. Okay, again, if you orient the fingers, you will find that so if thumb is pointed along east and forefinger along north, you will find that for a right-handed coordinate frame, the middle finger should be up. So the z-axis should be along local vertical but in the upward direction, east, north, up. So the corresponding frame is called east, north, up, ENU frame. Generally we use NED representations, but some authors prefer to use ENU representation also. So both are called local navigation frames. Now there is an important difference between this frame and the previous two frames. What is that? Now you just see the orientation of the axis as the origin moves on the surface of the earth. So this is how the axes are oriented when the origin is here at some latitude and longitude. And when the origin is on the equatorial plane, this is how north, east and down axes are oriented. So depending on the location of the origin, the orientation of the axis are changed, right? The XYZ axis orientations are changed depending on where the origin is. But that is not the case with the previous two frames. ECF frame XYZ directions are fixed. Irrespective of where the user is, XYZ axes are not changed. And the same goes for the ECI frame also. The frames whose coordinate axes do not change based on user location are called Cartesian frames, whereas the frames whose axis orientations change with user location or user position are called curvilinear coordinate frames. So local navigation frame is an example of a curvilinear coordinate frame. Okay. Now the notation is M. So often we are interested in finding the position of the origin because it is at the vehicle CG or some suitable point on the vehicle with respect to the ECF frame or ECI frame. Generally we are interested in ECF frame because that is attached to the earth. Okay. So this is the third frame. The fourth and the last one is called body frame. Notation is B. Origin is again at the vehicle CG or at some point whose position we want to determine. And then z-axis points downward. Okay, x-axis points along the forward direction of travel, and y-axis points right. So here we have shown the body frame for an aircraft. Okay. So these are the four different frames that we may need in this class. There are other frames as well, but we'll not go into those frames. Okay. Now we already discussed that we are interested in finding position or linear or angular velocity or acceleration. Right? These are all vector quantities. So we are going to use this notation in this class where x is the vector quantity. Okay. Beta in the subscript is the reference frame. So we are interested in finding position, velocity, etc. with respect to the beta frame. Okay. We are interested in finding this quantity of alpha frame. So alpha is called the object frame. So in the subscript, the left one is the reference frame and the right one is the frame whose position, velocity, etc. we want to determine, which is also called object frame. Okay. Now these are all vector quantities. So we need to resolve the three components along some coordinate frame, right? This gamma in the superscript is that frame. It is called the resolving frame. Okay. Now we can pick any frame for gamma. It can be beta, it can be alpha also, or it can be some other frame, some third frame, which is different from beta or alpha. Okay, that's why it is to have a generic representation. We are going to write the resolving frame in the superscript. Okay, so whenever we see a vector quantity with this representation, we will know that this is the reference frame, this is the object frame, and this is the resolving frame. So if you are interested in finding the position of the body frame with respect to ECF frame resolved along the axis of ECF frame, this will be E, B, E. If you resolve the components along the body frame, then we have to write E, B, B. Okay. Now we also can find attitude using a navigation system. For attitude, we do not have three frames. Okay, we just have two frames. So we are interested in finding the orientation of one frame with respect to another, right? So in that case, if it is attitude, then we'll just have two frames, the reference frame and the frame whose attitude we are interested in, whose orientation we are interested in. Okay, so in the superscript we write the reference frame, and in the subscript we write the reference frame, and in the superscript we write the object frame whose orientation we are interested in. So this is a convention that we are going to use in this class, and it is as per Paul Group's book. Okay. So any question? Have you understood how the frames are defined?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Next, we are going to talk about Earth surface model. So how we model the surface of the Earth for navigation purposes, and with that model we'll also define some important quantities, and then we we'll have two representations of position and we'll see how to go back and forth between them. Okay. For terrestrial navigation, we are interested in finding the position of a body with respect to the Earth's surface. Okay? But we also know that the surface of the Earth has irregular shapes, right? The terrain has irregular shapes. So if you want to capture the details, all the finer details of the Earth's topography, then we would require a large storage space and complex navigation algorithms. Okay. Now, as an alternative, we adopt two models for the Earth surface. They are called geoid and reference ellipsoid. Yeah. Now let me first pictorially show these two models. So let's say this is the topographic surface. Of terrain. Yeah. See. This is swimming sea level, okay? Swimming sea level. You have extended this swimming sea level to land, okay? And this one is geoid. And let's say this is ellipsoid. Okay. So this is a pictorial representation of these different models. Now, what is a geoid? So geoid is basically an equipotential surface the Earth's gravity field. Fitted to global mean sea level in a least square sense. This is a least square feet. So geoid is the least square feet to global mean sea level, and it's also an equipotential surface of the Earth's gravity field. I did not write gravitation. I wrote gravity. There is a difference between gravity and gravitation. It will be clear to you as we discuss this. So we take an equipotential surface of the Earth's gravity field and then fit it to the global mean sea level in a least square sense. Least square sense means we take the difference at different points on the Earth. We take the difference between the equipotential surface and mean sea level. Okay. So we get many differences because we consider different points on the surface of the Earth, and then we find the sum of square error. So if we have, say, epsilon is the difference at one point, then we square it and then sum all the squares. Okay. So this is called sum of square error. Okay, least square feet means we find the equipotential surface in such a way that this sum of the squared error is minimized. This is called a least square feet. Okay, so the geoid is fitted to mid sea level, global mean sea level, in a least square sense. Now, if the Earth's ocean surface is not perturbed by tides or some currents or weather, then it closely approximates the geoid. Okay, it is within a meter of geoid. Now, geoid is a relatively smooth surface. So, if you compare the geoid with the Earth's terrain, you will find that this yellow line here, this one. So this is relatively smooth surface, smooth and closed surface, but still it is not easy to mathematically represent it. Why it assumes a shape like this? This happens because of the uneven distribution of mass within and on the surface of the Earth. That's why we do not get a nice model that can be easily represented by a mathematical model. So the second one that can be used is called the reference ellipsoid. And why we pick this mathematical model, reference ellipsoid? Why ellipsoid? Why not sphere? Now it can be shown that a rotating fluid body, okay, under the influence of gravitation, assumes the shape of an ellipsoid in equilibrium. So let's try to understand why this is so. So let's first consider a fluid body, okay, and it is not rotating about its main axis, okay, it is stationary, but it is under the influence of gravitational forces. Okay. Now we also know that fluid particles have a tendency of going from higher potential to lower potential, right? So if the shape of the fluid body originally was like this, then there will be movements of fluid particles on the surface, correct? Until all the fluid particles are at the same potential, same gravitational potential, right? Now we know that gravitational forces act towards the center of the body. Okay. Now when all fluid particles are at the same gravitational potential, the resulting shape must be a sphere, right? Only when the fluid body assumes the shape of a sphere, fluid particles will be at rest, right? On the surface, there won't be any movement. So in equilibrium, the fluid body would assume the shape of a sphere when it is subjected to gravitational forces. So you have considered only the gravitational forces which act toward the center of the body. Now let's assume that this body also rotates about its spin axis. So each fluid particle is now subjected to two forces. The first one is the gravitational force which acts towards the center of the body. The second one is centrifugal force, correct? And the resulting force on each particle is the vector sum of the two, gravitational force and centrifugal force, right? So the resultant force will be something like this. We will draw it properly. So this is the gravitational force and this is the centrifugal force. So this is the resulting force, the middle one. This is the resulting force. This is centrifugal. And this one is gravitational and centrifugal. Now if we write this in the form of acceleration, we have gravitational acceleration and centrifugal acceleration, right? So if gamma is the gravitational acceleration and centrifugal acceleration will be, so let's say this is the earth rotation rate. Can use small number. R is the position of the particle at the point, this point, right? This is actually acceleration due to gravity. This is gravitational acceleration. And this one is centrifugal. Okay. Now, what will be the equipotential surface of the body when we consider both of these forces, gravitational force and centrifugal force? It can be shown that equipotential surface, which is normal to the resulting force, is an ellipsoid. This is why a good representation of the Earth's surface is an ellipsoid, not a sphere. Okay. Because you know that the earth was in liquid state after its formation, and then gradually it became solid uh, over time, right? So the best model, mathematical model that we can adopt to represent the earth's surface is reference ellipsoid or ellipsoid. So do you understand why we use an ellipsoid to represent the earth's surface, not a sphere?
Yes, ma'am.
Yes, ma'am.
Okay. Now a reference ellipsoid is one which is fitted to the geoid in a least square sense. Okay. So simply some ellipsoid will not have. We are actually finding that ellipsoid which is fitted to the geoid. Okay. Now this fitting can be done locally or globally. So let's say this is the geoid. So this is the geoid. Okay. Now if we find the reference ellipsoid by fitting it locally over some region of interest, we get a local reference ellipsoid. Okay, so this is also called a regional data. Now if we fit the ellipsoid globally, then we get a global reference ellipsoid. If the fitting is done globally, we get a global reference ellipsoid. Okay, now you can notice that a local reference ellipsoid is a good fit to the geoid over the region of interest over which it is fitted, but it is a poor fit elsewhere. Whereas a global reference ellipsoid gives an overall good fit. Okay, so it depends on what application you are interested in. If somebody wants to have the system working only over a particular region, then he can use a local reference ellipsoid. If the area of interest is all over the world, then a global reference ellipsoid would be uh, used. Okay. Now, how do you find the shape of the ellipsoid or the parameters of the ellipsoid? Now, if you notice carefully, you will see that this ellipsoid, we consider a global reference ellipsoid. The shape of the ellipsoid can be determined, since I am showing 3D into the, it appears to be an ellipse. But you just imagine an ellipsoid in 3D. And how do you get the shape of the ellipsoid in this particular case? So the shape of the ellipsoid is actually determined by the shape of the ellipse that generates the ellipsoid when it is rotated about its minor axis. So if we take an ellipse, this is the major axis, this is the minor axis, and then if you just rotate it, if you rotate it what we'll get? We'll get an ellipsoid of revolution, correct? At the reference ellipsoid. Any vertical section, cross section of that ellipsoid is an ellipse like this. So we can think of this as a vertical cross section. Of the ellipsoid. Now the parameters of this ellipse actually determine the shape of the ellipsoid. So let's define the parameters of the ellipse that generates the ellipsoid when it is rotated about its minor axis. So this is the major axis. This is major axis. And this one is minor axis. Okay. Now we use two parameters. The first one is equatorial radius. So this line is in the equatorial plane, horizontal line. The major axis is actually in the equatorial plane. So equatorial radius R naught. So this is R naught. So, and the second one is eccentricity. E. So RP is the polar radius. Sorry, RP. So this is eccentricity. In place of eccentricity, we can use another term called flattening. Okay, which is defined as 1 minus RP by R. So using these two parameters, we can determine the ellipse that generates the ellipsoid of revolution, or simply the reference ellipsoid. The first one is equatorial radius and the second one is eccentricity or flattening. Either eccentricity or flattening should be used. Both are not required. Now if we take a point somewhere on the ellipse whose coordinates are x, y and z, then its distance from the ellipsoid center, okay, is called geocentric distance r. Right? So in 3D, if we take the point somewhere on the ellipsoid, this distance, its coordinates are x, y, z. So we are basically connecting that point with the center of the ellipsoid, and this distance is r. R is called geocentric distance, okay, and it is given by square root of x square plus y square plus z square. Now the same point is shown here on the vertical cross section. So if we take a cross section, vertical cross section of the ellipsoid passing through that point, we get this ellipse on the left side. Okay. Now, if we project R, this line, on the equatorial plane, we get this distance. Right? So, in the 3D representation, this is the equatorial plane. We project the point on the equatorial plane. Right? And this distance, this green line on the equatorial plane is actually shown by this line. Are you able to follow? Because this visualization is important here. How we are going back and forth between 2D and 3D representations. If you do not follow this, then you will not be able to visualize things properly. Okay, so this distance, which is the distance of the projection of this point from the center, is called beta. Okay, so let's denote it as beta. So beta square is actually x square plus y square, right? What is the ellipse equation? Ellipse equation is, can you tell me the ellipse equation?
X square by R naught square plus y
No,
square.
I have already given you the variables here, right? So you need to tell me the equation. So let's say this is z and this one is beta. So you need to tell me the ellipse equation using those variables. So tell me the ellipse equation using the variables that I have shown on the left side. So you're telling me some equation in terms of x and y. So why don't you replace x and y suitably?
With beta and z.
And then tell me.
So then beta square by R naught square plus z square by RP square equal to 1.
This is the ellipse equation. Now if we replace beta with this one, what do we get? So the ellipse equation is I know beta square is equal to x square plus y square. So if we replace beta with this one, we actually get the equation for the surface for the ellipse side. So x square by r naught square plus this one. And in this right figure, we actually used a coordinate frame to show x, y, z. Right? This coordinate frame is attached to the arc, so it is an LCF frame. Yeah. So x, y, z coordinates are actually obtained in the LCF frame. Okay. Now, two main standards for the global reference ellipsoid are the World Geodetic System, WGS 84, okay, and the International Terrestrial Reference Frame. ITR. You'll understand why I'm discussing this. Originally, ITRF was more precise than the WGS 84 standard, but WGS 84 underwent several revisions in the 1990s, and after that, it is in close agreement of the ITRF standard. Okay? So they are now equivalent. WGS 84 and ITRF, they are almost equivalent. Both the standards have their origin at the Earth center of mass. So the ellipsoid center is at the Earth center of mass, okay, and define the Earth rotation using the IRS reference point. So both of them have the ellipsoid center at the center of mass. And they define Earth rotation using the IRS reference point. Okay. GPS, both GPS and IRNSS, GPS and IRNSS use WGS 83. Okay. Most INS, Inertial Navigation Systems, use WGS 84 as the reference ellipsoid. So the position of any body is actually provided with respect to the reference ellipsoid, and GPS and IRNSS use the WGS 84 reference ellipsoid, and most INS also use INS systems also use the WGS 84 standard as the reference ellipsoid. Okay, but other satellite navigation systems have their own standards. For example, GLONASS, the Russian system. GLONASS has PZ90. This is a different standard they use. Basically, it's similar to WGS 84, but the center of the ellipsoid is off from the center of the WGS 84 reference ellipsoid. Then Galileo has another reference ellipsoid, which is actually a realization of the ITRF. Then way do the Chinese system has an equivalent standard, which is in close agreement of the ITR. Okay, so it's not necessary that all satellite navigation systems will use the same reference ellipsoids, but one needs to know uh, what reference ellipsoid is used, because each constellation can give the user position, but if they use different reference ellipsoids and you want to combine measurements from all the different constellations, then you need to take this into account. Otherwise, the position that you will get would be wrong. Okay, so it's important to know which satellite navigation constellation uses which reference ellipsoid. Since GPS and IRNSS use the WGS84 reference ellipsoid, let me tell you some more parameters of the WGS84 reference ellipsoid. So, the equatorial radius of the WGS84 reference ellipsoid is 60. 6378.37 meters. Okay, this is the equatorial radius, and instead of giving the eccentricity, it defines flattening. Okay, the flattening is 1 by 298.257 to 3563. This is the flattening. So apart from this, the WGS84 also defines RECF coordinate frame. Then it provides a geoid model or geoid table. So this basically gives the difference between geoid and ellipsoid, reference ellipsoid, as a function of latitude and longitude. So, the geoid model is also defined, and Earth's gravitational model is also provided. In the gravitational model, the gravitational acceleration is defined as a function of latitude and altitude. You don't think that it is simple formula. No, they consider higher order terms and show how the gravitational acceleration changes with latitude, considering higher order terms. So these are called harmonics. So the model includes gravitational harmonics, higher order terms. It's a function of latitude, and then for altitude variation we just use that inverse square law. Okay, so all these different things are also defined in the WGS 84 standard, and the same goes for other standards as well. Okay. Now we have two models, right? One is the geoid, another is the ellipsoid. So this is the ellipsoid and this is, let's say, the geoid. So at each point we can find the distance between geoid and the ellipsoid. So this is the normal distance. Okay, so this is called geoid height. It's denote this as King. Okay, and it is a function of latitude and longitude. So L is latitude and lambda is longitude. Okay. The geoid height is the normal distance of any point on the geoid from the ellipsoid. Is basically defined in the geoid model as a function of latitude and longitude. Now the height of a point above the geoid is called orthometric height. So it is the normal distance of the point from the geoid. So this is called orthometric height. And the height of the same point from the ellipsoid is called geodetic height. Okay, so let's denote the geodetic height as small h d and orthometric height as capital H d. Now we can relate capital H d for body to H b approximately as follows. So this is the orthometric height. I'm writing O. This is geodetic height and this is geoid height. Okay, this is approximately true because you can see that the directions are different, right? Normal to geoid may not coincide with normal to ellipsoid. Right? That's why I put this approximation sign here in the equation. And L and lambda are the latitude and longitude of the point. Now, why am I telling you this? Because you get height from GPS or any GNSS system, but what height is that? Actual height that we get from the GNSS system is the geodetic height. So the system actually determines the geodetic height. But different applications may require orthometric height. In that case, we have to use the geoid table to go to the orthometric height. For example, in case of mapping, we require orthometric height. We are interested in finding the height of the point above geoid. So then we need to calculate the orthometric height. But the system actually gives geodetic height. Then internally, it has to use the geoid table, okay, to convert the calculated or estimated geodetic height to orthometric height. Okay, let's have a 5-minute break now. We'll continue after the break. It is 14 past 12 now. So we'll resume our discussion at 19 past 12. Okay. Next, we are going to formally define latitude and longitude. We already defined height. Since we are going to define latitude and longitude with respect to the reference ellipsoid, the corresponding height here would be the geodetic height. Okay. So let's say we are interested in finding the latitude of this point, whose geodetic height is h. So geodetic height is nothing but the normal distance of the point from the reference ellipsoid. Okay. Now, if we extend the normal from the body to the ellipsoid surface, it intersects at this point. So it intersects the ellipsoid surface at this red point. Correct. Now, latitude is the north-south angular distance of this point. So let's call this point B, and then this point C. The latitude of B is actually the north-south angular distance of C. So latitude is the north-south angular distance of the point where the normal intersects the ellipsoid. In this particular case, it is point C. Now we can calculate this angle in two ways. The first approach actually connects C with O. Okay, and find the angle that this line CO makes with the equatorial plane. So this angle is denoted as phi. Phi is called geocentric latitude. The second approach is to extend this normal, this is the normal, further and find the angle that the normal makes with the equatorial plane. This angle is called geodetic latitude. Okay. Now, phi and L are related as where E is the eccentricity. So WGS 84 standard gives us flattening, from which we can get the polar radius because we know the equatorial radius. And then using the polar radius and equatorial radius, we can find the eccentricity. So although eccentricity is not given, we can calculate it using the equatorial radius and flattening. And this is how the geocentric latitude is related to the geodetic latitude. In this class, we are interested in geodetic latitude, okay, not geocentric latitude. But we can always calculate the geocentric latitude from the geodetic latitude using this equation. Okay, so actually we are interested in geodetic height and geodetic latitude. Next, we will formally define longitude. And the notation is lambda. We have the reference ellipsoid, and this is the equatorial plane. This is the center of the ellipsoid. This is the earth spin axis or z-axis. And this dashed line shows the IRS reference meridian. So this is x-axis, PCF x-axis, and then this is y-axis. Now, this is point C that we considered on the previous page. So how do we find the longitude? So we draw the meridian that passes through this point C, and the angle between this meridian and the reference meridian is longitude on the equatorial plane. Okay, so the longitude is the angle between the meridian containing the point of interest and the IRS reference meridian in the equatorial plane. Okay. Now, as a body moves in the north-south direction, the latitude changes, right? This is why we say latitude is the north-south angular position. In other words, we can associate latitude with the north axis of the local navigation frame, correct? Similarly, when the body moves east in the east-west direction, the longitude changes, right? So you can associate longitude with the east axis of the local navigation frame, correct? And then when it moves up or down, the height changes, correct? So we can associate height with the z-axis or the down axis of the local navigation frame, down or up axis of the local navigation frame. So basically, latitude, longitude, and height can be associated with the northeast and down axis, correct? Now we also noted that the northeast and down axis are actually curvilinear coordinate frame. Therefore, latitude, longitude and height are called curvilinear position. Okay. So lat, long and height. Are called curvilinear position. Whereas ECF XYZ coordinates of the body. So you can find the XYZ coordinates of the body. When we say body, we are interested in so there will be a body frame and we are interested in finding the position of the origin of the body frame. So if we find the position in the ECF frame, we get XYZ coordinates. And coordinate frame axes do not change their orientation. So it's basically Cartesian coordinates, XYZ position we are getting. So ECF XYZ or ECF position is Cartesian position. So we can represent or find the position of a body either in curvilinear frame, curvilinear coordinates or Cartesian coordinates. Okay. Next we are going to define two radii of curvature. Had this arc been a sphere, we would have required only one radius. But since it is an ellipsoid, we need to define some suitable radii of curvature. Okay, we'll define the radii of curvature and then we'll see how to go back and forth between ECF Cartesian position and latitude, longitude, height, the curvilinear position. So we are going to find the relations between the Cartesian position and curvilinear position after we define the radii of curvature, because we require the radii of curvature to find the relations. So we start with the basic definition of a radius of curvature. What is curvature? Curvature is actually a measure of how much a curve is deviated from a straight line. Okay. So the notation is K. Let's consider the curve like this, and we are interested in finding its curvature at this point. So we take another point at an infinitesimally close distance, and the distance between these 2 points is ds along the curve. Okay. And then find, so at this point, at the rate point, this is the tangent to the curve. And at the blue point, this is the tangent to the curve. Okay. And then we find the tangent, the angles that the tangents make with some reference direction. So this white horizontal line shows the reference direction. Then this angle is phi. Okay, and this angle is phi plus 3 phi. So the curvature is given as this change in phi over distance ds. or per unit distance ds along the curve. So this is curvature. When the curve is actually a straight line, d phi would be 0, right? And curvature is 0. The radius of curvature r is actually the reciprocal of k, right? So for a straight line, the radius of curvature is infinity, correct? So this is the basic definition of or radius of curvature. Now, in the case of reference ellipsoid, we define two radii of curvature. The first one is called meridian radius of curvature. So it is used for north-south motion. Now, how do we define this? So this is the reference ellipsoid. These are ECF XYZ axis, and this is the point of interest. We want to find the north-south or meridian radius of curvature at this point. So what we do is, we take a cross section of the ellipsoid in the north-down plane, or basically a vertical cross section of the ellipsoid. So this is north, this is down, and this is east. So if we take a vertical cross section of the ellipsoid passing through this point, we get this ellipse. We are actually taking a vertical cross section of the ellipsoid. So you just pass a vertical plane through that point and take the cross section of the ellipsoid. So it is an ellipse. So this is the cross section of the ellipsoid in the north-down plane passing through that point. Now why do we say north-down plane? See, if we take a vertical cross section of the ellipsoid, it will always contain the earth spin axis and the center of the ellipsoid, correct? And then you just take that point, this point here. This is north, correct? And this is down. So this cross section of the ellipsoid contains the north and down axis. That's why we say that this is the cross section of the ellipsoid in the north down plane. Okay. Now at this point we find the best fitting circle to the ellipse. So this blue circle is the best fitting circle to the ellipse at that point. And the radius of that circle is the meridian radius of curvature. Okay, this definition is equivalent to what we define on the previous page as the basic definition of radius of curvature. Okay. So it is the radius of the best fitting circle. in the north down plane of the ellipsoid. At the point of interest. How do we find the base fitting circle? So on the previous page, we found the basic definition. We defined curvature and got the basic definition of the radius of curvature. Now, for any curve, y is equal to f of x. It can be shown that this one changes to okay. So the curvature for a curve given by this equation y is equal to f of x is this equation, which can be shown from the basic definition of curvature using this equation y is equal to f of x. Okay. How do we find the base fitting circle of the ellipse at that point? The base fitting circle has the same curvature as the curve at that point. So both the ellipse and the circle would have the same curvature at that point. So how can they have the same curvature? d square by dx square should be the same for both, and dy by dx should also be the same for both. Okay. Now how do you find this circle? To find the circle, we need the coordinates of the center and the radius, right? So we have x and y coordinates and the radius, three unknowns, right? So to uniquely define this circle, we require three equations. Now we already have the ellipse equation and the circle equation. So at this point they are the same, correct? So we can equate the two equations because x and y coordinates are the same, correct? And since the curvature of the base fitting circle is the same as that of the ellipse, d square by dx square will also be the same, and dy by dx will also be the same. So we have to equate the ellipse equation and the circle equation. Then we also have to find the first derivative and second derivative and equate them. So basically we get three equations, and using these three equations we can find the three unknowns. So this is how we can uniquely define the base fitting circle, which has the same curvature at the point of interest. And then the reciprocal of the curvature would give the radius, right? Since they have the same curvature, the radius of the circle is actually the radius of curvature of the ellipse at that point, right? So the meridian radius of curvature is the radius of the base fitting circle of the point of interest in the north down section of the ellipsoid. The other radius of curvature is called transverse radius of curvature. If you have any question, if you did not follow anything or you are having any problem visualizing things, ask me. Okay. Otherwise, I will not know where your stuff are. where you are finding things difficult. So feel free to stop me and ask your question. Okay, the notation for the meridian radius of curvature is Rn. Okay, and in case of the reference ellipsoid, Rn is a function of latitude. It is R0 equatorial radius minus E square divided by 1 minus E square sine square N. Okay, this can be shown using this formula and the ellipse equation. The notation for the transverse radius of curvature is RE. To use this curvature, radius of curvature for east-west motion. But don't think that this radius of curvature is defined by taking a section of the ellipsoid in the east-west direction. No. Rather, we take a cross-section of the ellipsoid in the east-down plane. So we have the ellipsoid. This is the point. This is north. This is east. This is down. Earlier we took a section in the north down plane, meaning the plane contains the north and down axis. Now we take a section of the ellipsoid by passing a plane through it, and the plane contains the east and the down axis. You just think of a plane containing the east and down axis, and it passes through the ellipsoid. It can be shown that if we pass a plane through an ellipsoid, the cross section that we get is an ellipse, irrespective of the orientation of the plane. So whether you pass it horizontally, vertically, or in some inclined manner, you will always get an elliptical cross section. Of course, the shape of the ellipse will be different, parameters would be different depending on the orientation of the plane, but you will always get an elliptical cross section. This can be shown mathematically. Okay, it's not a straightforward proof, but I actually had seen a paper where they had given detailed mathematical proof and showed that whatever be the orientation of the plane, the resulting cross section of the ellipsoid is always an ellipse. So in this case also, the east down plane cross section of the ellipsoid is an ellipse. Okay, and then we can apply the same definition as before. The radius of the best fitting circle at the point of interest in the east down cross section of the ellipsoid would be the transverse radius of curvature. Okay. Now, see, whenever we are defining the radius of curvature, it is always along the down axis. Why? Because by definition, the radius of curvature must be normal to the surface of interest. Here, the surface of interest is the ellipsoid, and the down axis is actually the local vertical. It's normal to the ellipsoid. So the radius of curvature is always defined along the down axis. That's why we cannot take a section in the east-west direction that does not contain the down axis. Either we have to take the cross section in the north down plane, or we have to take the cross section in the east down plane. Okay. So when we take the cross section in the east down plane and find the best fitting circle at that plane, we get the transverse radius of curvature, RE. The expression of RE is R naught Now it is difficult to visualize, right? The north down, the meridian radius of curvature could have been visualized because we could visualize the meridian radius of curvature easily because we took a vertical cross section of the ellipsoid. But here we need to take an inclined cross section, right? So it is a little bit difficult to visualize this radius of curvature. But fortunately, it is possible to show this radius of curvature in the north down plane as well. How? So this is the vertical cross section of the ellipsoid in the north down plane. Okay, and this is the local vertical. This is north. This is down. So just extend this local vertical or down axis further so that it intersects the minor axis of the ellipse. Okay, then this distance is RE. So we denoted this point as so let's call it C and this D. So CD is actually D. Now you have a homework problem here. So you need to justify that CD is RE. Now an easy way to show this is to find geometrically the length of CD and show that it is equal to this one, and then from there you can conclude that it is equal to RE, but I am not looking for that explanation, okay? So there you assume that RE is equal to this, and then you show that the length of CD geometrically is equal to this one. This is not what I am looking for. Using the basic definition of radius of curvature, you can use some other equation, but not the expression of RE. Okay, you need to justify. I'm not asking you to prove it, but you need to justify that the length CD is actually RE. So is the question clear to you? If not, ask me now. Don't tell me I did not understand it later. Have you understood what I am looking for? I'm not asking you to show that the length CD is equal to that expression. I'm not asking you to do that. You need to prove using the basic definition of radius of curvature that CD is actually the transverse radius of curvature.
Yes, ma'am, understood.
Okay, next I'll show you how RE and RN vary with latitude. So here interested in the variation with geodetic latitude, capital A. And along y-axis we are plotting the two radii of curvature Rn and Re. So this is 0 degrees and this one is 90 degrees. And this length is Rp, polar radius. And let's say this one is Rp, which is 6378.137 kilometers. And this length is another one, which is 6400 kilometers. Okay. Then Rn goes like this. And Re goes like this. So when L is equal to 0, Re is actually this is okay. So this is how they vary with latitude, meridian radius of curvature and the transverse radius of curvature. Now, which radius of curvature will you pick when you move in an arbitrary direction? So in the northeast plane, this is north, this is east. So suppose you move in this direction, that the direction of travel makes an azimuth angle psi. Which radius of curvature will you pick? So for any arbitrary direction of travel with azimuth psi, the radius of curvature is given as this can also be shown. So for any arbitrary direction of travel, we can find the corresponding radius of curvature using the azimuth angle and the two radii of curvature. Okay. How much time is left? 3 minutes only. So I'll just start that derivation. Will not be able to complete this. We'll continue in the next class, but I'll start it now. So we are interested in finding the relations between Cartesian and curvilinear relations. So basically, given ECF XYZ coordinates, we want to find lat, long and height, or given lat, long and height, we want to find ECF XYZ coordinates. This is what we want to do. Okay. We have the reference ellipsoid here. ECF XYZ axis, X, Y, Z. This is the equatorial plane. Okay, and we take a point at some geodetic height h. The normal from the point to the ellipsoid surface intersects the surface at this point. Here, this is h. Okay, and then we take the vertical section of the ellipsoid passing through that point. Right? If we extend this line further, it intersects the equatorial plane at this point. This is lambda, and this angle is, what is this angle? What is this angle? Tell me what this angle is. You understand that this angle is lambda? You understand this?
Yes, ma'am.
And what is this angle?
Eta.
So this is theta. You see the variable notation we have used. Have you used theta anywhere?
Phi.
How it is phi? What is phi? What do you mean by phi?
The geodetic angle.
Geodetic. Is this geodetic? Sorry. Phi is the notation for geodetic latitude. What is the notation for geodetic latitude? What is the notation for geodetic latitude? And which one?
L.
Then did I write phi there? I did not write phi there. So this is L.
Yes, ma'am.
This is L, correct? Now if we see the knot down section, this distance is h, and then we extend it further. This angle is L. This is the minor axis. We extend further, and this length is nothing but RE. This is RE, right? And this distance is Z. Basically, it is difficult to show it in the 3D. On the left figure, this is the arc spin axis. So this and the Z axis here, Z axis is along the arc spin axis. So this is the Z coordinate. This line is in the equatorial plane. This is in the equatorial plane. So this distance is Z. Basically, we need to draw projection of this point on the equatorial plane. And that distance is shown here. This one. So this is Z. At first we will find x, y, z given latitude, longitude and height. So we assume that height is given, this distance is given, latitude is given, longitude is also given. So given lat long height, we want to find the PCF XYZ coordinates. Okay, so that's it for today. We didn't have time to solve the tutorial problems. Next Wednesday is a holiday, so we'll meet again next Thursday. Next Thursday we'll quickly do the derivation uh, and then move on to the next topic. And you need to tell me how to solve all the problems, homework problems in the next tutorial class, which would be held next Friday. Okay, so I gave you 3 problems last Friday, and today one more problem. In fact, instead of doing this derivation in the class, I will give you it as a homework problem. So what you do is, you find given lat, long and height. So this is another homework problem. Find the x, y and z coordinates. You have to use simple geometry to find the Cartesian position from the Carbonian equation. Okay, so this is another homework problem. So we basically have 3 from last week and 2 from this week. So total 5 homework problems you have. You need to tell me how to solve them next Friday in the tutorial class. Okay? Any question? Anything that you did not understand and want me to clarify again? So you understood the last homework problem? You can visualize latitude, longitude and height.
Yes, ma'am.
Any question?
Yes, ma'am.
Yes, ma'am.
Anything that you did not follow? Because here you need to visualize things in 3D. You are drawing it in 2D, but actually it is in 3D. So some people may find it a little difficult to represent 3D in 2D. That's why I'm asking repeatedly. You understood both the radii of curvature? Why the radii of curvature should be along the down axis? Why we cannot take a cross section of the ellipsoid in the east-west plane? Why it has to be either north down plane or east down plane? That understanding is important. I told you to justify why that length of the normal is the transverse radius of curvature. So to justify this, you need to visualize things properly. Okay, fine.